In this video, I'm going to teach you how to find the algebraic rule for the inverse function. We've looked at graphing inverses, and all we need to do to graph inverses is to change the ordered pairs around. In this part, what I need you to do is be able to find the rule for the inverse function. So we're going to go from the idea that if we have a function, the function is going to give us an xy ordered pair. But if we graph the inverse function, we know we need to turn the question around, which means the output becomes a new input and the input becomes a new output. We reverse the idea. Well, that's the same thing that we do when we find the rule algebraically. So if our function rule is defined to be x minus 3 divided by 5, then in order to find the inverse of this, we have to switch the roles of x and y. Well, that's a little bit of a problem because we don't see a y, but f at x represents your outputs, your y's. So we're going to make the first substitution of taking out the f at x and replacing with the output variable y. Now we're going to switch the roles of x and y. To find the inverse, we need to make sure that the x and the y roles get reversed, all over 5. Now when we find a rule for an inverse function, we always want to solve it for y because y by the very nature should be the output and x's are the inputs. So we're going to solve this for y. That means we're going to multiply both sides times 5, which means 5x equals y minus 3, and then I have to add 3, so that means y equals 5x plus 3. Now this y that we just solved for is supposed to represent our inverse function. And we have a name, or at least a way of denoting the inverse function. That means we're going to go back to, it was a function f, but we found the inverse of function f. Now this is the algebraic rule that is the inverse of our original rule of function f. Function f was the rule that said we had x minus 3 all over 5. These are inverses. And because they're inverses, if I look at their graphs, they would have to be symmetrical to the line y equals x. If I looked at their ordered pairs, the ordered pairs would have to be for every xy, there has to be a y comma x. So I'm going to try to look at decimals here with you and show you that this function rule that we found really is the inverse of our original function. So our original function was, getting it to the screen that I need, this is our original function, y equals x minus 3 over 5. I'm going to show you some ordered pairs of this function rule by clicking on that. So here are the ordered pairs in a table, and I also have them shown on the graph. So this is the ordered pair 2 and negative 0.2, and this is the ordered pair 1 and negative 0.4, right down the line. If I put them all on there, they get kind of messy, so I'll just put a few on there. Actually, I'll put those on here like this, leave that one off. Now, if we were to graph these, we'd have to flip the nature of these ordered pairs. So if I flip those ordered pairs or switch them, then I'd want to graph the ordered pair negative 0.22, and I'd want to graph the ordered pair negative 0.60, and I'd want to turn that other ordered pair around, that negative 2,1. It doesn't appear that I had that one in there, so I'll just add it, and I'll graph it as a negative 1 comma negative 2. And it's going to be a black dot, but that'll be fine. Okay, so now if you notice that these points here seem to lie on the same path, and I'm going to plot the graph that we said should be the function rule for all the inverses. And notice that that dashed or red line goes through all the points that we have of our original function, but in reverse. And that's how we graph inverses. We flip their ordered pairs. We also want to make sure that it does have symmetry about the line y equals x. And if I put the line y equals x in there, you can see how these points get reflected across the line y equals x. So there's some graphical evidence of what they are, so we're going to go back to what they asked us to do in this problem. They said find the inverse function. We just did. And then it says then graph the function its inverse, which I showed you the graph of the function its inverse, and it's symmetrical to the line y equals x. Okay, so now I'm going to do the second example here with you. And it's a little bit more involved because of the nature of it, but it's the same procedure. First thing we do is we're going to take our function f at x equals 3x squared, and we're going to replace the f at x with a y. So now we got y equals 3x squared. Then we change the roles of x and y. So the x's must become y's and the y's become x's for inverses. So x equals 3y squared. Once we've replaced the x's and the y's, we solve this for y. So that's going to make us divide by 3, so it's going to be 1/3 x, or x over 3, equals y squared. we have to undo squaring, and to undo squaring, you have to do the square root. So y equals plus and minus the square root of 1/3 times x. So this is our inverse function, so plus or minus the square root of 1/3 x should equal f inverse at x. Make sure I didn't lose track of this. So this is the inverse of the function that we started with, which was f at x, which is defined to be 3x squared. So we found the rule algebraically, so now if I graph this rule along with this rule, we should see that they are symmetrical throughout the line y equals x, and we should also see that every ordered pair that's in the inverse should be the switch rule of our original function. So graphical evidence one more time on that. We'll go back to Desmos. It gives a nice clean picture of this. Getting organized here, and now let's come up and grab our function. Y equals 3x squared is a parabola. I'm going to graph some specific ordered pairs off of it. There are my 3 ordered pairs that I selected to highlight out of that whole table. In order to graph its inverse, we would want to graph the flip of those ordered pairs. So the 1, 3 becomes 3, 1. The ordered pair 0, 0 still 0, 0. And the ordered pair negative 1, 3 becomes 3, negative 1. So we should have a shape that's coming from this point through the origin 0, 0, then coming right back over here through our ordered pair 3, negative 1. So there's no way to put in decimals plus and minus, so I had to put them in separately. There's the positive square root of 1/3 x, and here's the negative square root of 1/3 x. And if you look at those rules, are they still symmetrical to the line y equals x? So I put in the line y equals x. Now I'm going to get that out of the way and just kind of zoom in a little bit. And if you can see that this point here, this 1, 3, is being reflected across the line y equals x, and it's 3, 1, and this negative 1, 3 becomes 3, negative 1. So there is my graph, and that's the nature of the graph. They are both reflections across the line y equals x. And I've just shown you in this video how you can find the inverse function of any given function, and then how the graphs are related. So in recap, here's what we're going to do to find the inverse of any function. So the first thing I'm going to do is I'm going to replace f at x, g of x, or whatever with y. The second thing I'm going to do is I'm going to swap, for lack of a better word, the roles of x and y. So we're going to interchange those. Third thing we're going to do is we're going to solve that equation for y. And the fourth thing we're going to do is we're going to replace the y value with the inverse notation f inverse of x. So these are the 4 steps of finding the rule algebraically. I gave you a couple of examples of modeling how that is done. So when they ask you to find the inverse, that's what you should be doing.